If we knew the position and velocity of every particle in the universe, could we calculate not just tomorrow, but the next lottery numbers as well? Scientists have been debating this question for over 200 years. And the answer is far more interesting than you might think. Because the problem isn't luck, it's information. And yes, there really is a scientific path to the grand prize. But first, we need to dive a little into physics. By the end of the 18th century, mathematics and physics were filled with an almost intoxicating confidence. Newton's laws of motion and universal gravitation worked, not just approximately, but spectacularly well. They described objects falling on Earth and planets moving through space using the same equations. Cannonballs followed predictable trajectories. Moons orbited their planets exactly as calculated. Planets revolved around the sun precisely as expected. Nature no longer seemed mysterious. It looked like a perfectly functioning machine. It was in this intellectual climate that the French mathematician Pierre Laplace introduced one of the most radical ideas in the history of science. Not a theory, not an equation, but a thought experiment. Laplace proposed the following. If a hypothetical mind could know, at a single instant, the exact state of every particle in the universe, from the smallest to the largest, including their positions, their velocities, and the physical laws governing their motion, then for such a mind, the past would hold no mystery, and the future would contain no uncertainty. Because according to classical physics, the laws of nature are deterministic. That is, the same initial conditions will always produce the same outcome. Under this assumption, the entire history of the universe, past and future, could in principle be read from a single mathematical framework, a single vast calculation. Laplace gave this hypothetical entity a name, Laplace's demon. The word demon here is not religious. It is a metaphor for superhuman computational power, perfect measurement, infinite precision, and unlimited processing ability. In Laplace's universe, there is no randomness, there is no luck, there is no uncertainty. There is only lack of information. From this perspective, what we call chance is not a property of nature, but a consequence of human ignorance. And under this view, even lottery balls are not truly random. Their motion is fully determined by collisions with air molecules, microscopic imperfections on the ball's surface, vibrations in the machine, tiny variations in the local gravitational field. These factors are not random. They are governed by physical laws. We call the outcome luck only because we cannot measure all these variables simultaneously with sufficient precision. So according to classical physics, the lottery is not random in theory. It is simply overwhelmingly complex. We can understand this better with an example. Imagine a four-way intersection. Cars are approaching from every direction. Now imagine you somehow already know which car has brakes that barely work, which driver is texting instead of looking at the road, the car's speeds, tire conditions and braking distances, and whether the road is dry or slick from the rain. At that point, you wouldn't just predict that an accident might happen, you could predict which car will hit which one. And roughly how many seconds later, that's no longer a guess. That's a high probability scenario. And here's the slightly uncomfortable, slightly funny part. We're not the ones doing this right now. Others already are. Your phone knows. When your attention starts to drift, when you slow down, when you suddenly speed up for no good reason. But let's be honest, tiny, highly specialized demons are already hovering right behind you, taking notes, running statistics, and waiting for you to scroll just a little bit more. Before we talk about how to scientifically predict lottery numbers, we need to wrestle with something first. By the 20th century, the first major blow landed on Laplace's perfectly clockwork universe. Its name was quantum mechanics. When scientists began exploring the subatomic world, they realized something unsettling. Nature is not as clean, sharp, or certain as we once believed, and this point is crucial. The uncertainty here is not a failure of measurement devices, a lack of technological sophistication, or a problem we'll solve someday with a better microscope. The uncertainty is built into nature itself. This idea is captured most clearly by the Heisenberg uncertainty principle. It states, the more precisely you know a particle's position, the less precisely you can know its velocity, momentum. And the reverse is also true. This is not a practical limitation. It's not a we'll fix it with better equipment kind of problem. It is a hard limit imposed by the universe. But the truly mind-bending part comes next. One of the most confusing and most important facts about quantum mechanics is this. We don't merely observe particles. To observe them, we must interact with them. In the subatomic world, there is no such thing as just looking. To see something, you must send something. A photon, a packet of energy, an interaction, and that's exactly where the problem begins. Particles are so small that the photons we send to observe them are not a gentle tap, they are effectively a collision. So what we actually do is this. We ask, "Where are you?" And at the exact moment we ask, we push the particle out of place. That's why a particle state, before observation and after observation, does not have to be the same. And this is why a particle appears to be in one place when observed and somewhere else when it is not. We think of it this way. Imagine a billiard table. There's a tiny billiard ball sitting still. Now imagine trying to determine its position by firing another billiard ball at it. The ball hits. And of course, the first ball moves. Then you turn around and say, "Look, there it is." Yes, but there's a small detail. You're the one who sent it there. This is exactly what happens in the quantum world. Particles are so small that even the light we use to observe them disrupts the entire system. Measurement, therefore, is not passive observation, but active intervention. This is why quantum mechanics tells us a particle's true position does not have to be a fixed point independent of measurement. When we measure, we force one outcome out of a cloud of possibilities. And this is catastrophic for Laplace's demon, because Laplace's demon demands this: to know the position and velocity of every particle at the same time, without touching, without disturbing, without changing anything. But quantum mechanics is brutally clear. To obtain that information, you must interact with the particle, and the moment you do, you destroy the very information you're trying to preserve. So Laplace's universe stops being a problem that can be solved with enough data. But the story doesn't end here, because at this point, a perfectly reasonable thought appears. Fine, the subatomic world is weird, but we don't live our lives at the quantum scale. And this is where the real surprise begins. Because in the macroscopic world, cars, weather systems, financial markets, crowds, human behavior, just when we think we've escaped quantum uncertainty, we encounter another monster. Not one that feeds on uncertainty, but one that feeds on extreme sensitivity. Chaos theory doesn't say that everything is random. In fact, it says almost the opposite. For a long time, science thought the same way. Quantum mechanics was weird, sure, but daily life still belonged to Newton. The rules were clear, the equations worked, everything seemed calculable. Then scientists realized something uncomfortable. A system can follow rules perfectly and still be impossible to predict. That's exactly what chaos theory tells us. Chaos doesn't mean randomness. Chaotic systems follow clear rules but are extremely sensitive to tiny differences at the start. A very small change in the beginning can grow into a massive difference later. The classic example is the weather. We know how weather works. We know the equations. We know the physics. And yet, we can't reliably predict the weather weeks in advance. Why? Because if today we measure the wind speed just a little wrong, or miss the temperature by a tiny amount, those small errors grow over time until the outcome looks completely different. The problem isn't ignorance, it's precision. The same thing happens in everyday life. At an intersection, one driver braking half a second late, another checking their phone for a moment, can completely change what happens next. That's why chaos theory says to make accurate long-term predictions, you would need almost perfect information. But in the real world, measurements are limited, tiny errors are unavoidable, and those tiny errors eventually destroy the prediction. That's why traffic, lotteries, weather, markets, they all follow rules in theory but are unpredictable in practice. And here's the key idea: even without quantum uncertainty, chaos alone is enough to make the future impossible to calculate. So the universe is basically saying, knowing almost everything still isn't enough. And this is where the story turns, because in some cases, we can still make useful predictions without perfect information. Not by defeating chaos, but by working with it. Lottery numbers are hard to predict, but winning a prediction-based competition, that's where science steps in. If you're making predictions alone, chances are you'll be wrong. But when thousands of people make predictions together, the result becomes surprisingly accurate. Science has a name for this, and it's just one phrase: the wisdom of the crowd. The year is 1906, England, a public fair. At the center of the crowd stands a large ox, sometimes described as a cow, depending on the source. A competition is announced. How much does this animal weigh? The rules are simple. Whoever gets closest to the correct weight wins the ox. Hundreds of people line up: farmers, butchers, merchants, curious onlookers. Each person writes one number on a piece of paper. No one measures, no one weighs. Everyone relies on what they see, what they've experienced, and what they instinctively feel. The guesses are collected. Individually, they're a mess. Most are wrong. Some are extreme. Some wildly optimistic. Others overly pessimistic. Watching the scene is British statistician Francis Galton. His first thought is simple. The crowd will be wrong. But then he does something different. He calculates the average of all the guesses. And that's when something remarkable happens. The collective estimate comes out almost exactly equal to the animal's true weight. The closest answer comes from the crowd itself. No single person knew the correct answer, but each person knew a small piece of it. When those pieces were combined, individual errors cancelled each other out, extremes balanced, noise disappeared. What remained was a result astonishingly close to the truth. This moment revealed something profound. Under the right conditions, crowds can be smarter than individuals. It looks like magic, but it isn't. It's statistics. Because the more independent information you add, the closer the result moves mathematically toward reality. And that's where the idea we now call the wisdom of the crowd was born. We can improve the odds with math. We can be smarter with strategy. But for lotteries and pure gambling, we still don't have the knowledge or the tech to beat luck itself. Maybe for our grandkids, it'll be a classroom equation. For now, enjoy the mystery. That uncertainty is half the fun. If you enjoyed this video, don't forget to subscribe to our channel and hit that like button and share it with the people you care about, so the light of science can reach everyone.